the second class of optimal design of queuing systems. So I'll just do a short recap of what we did yesterday. Uh, so we'll be mainly following two books. One is Optimal Design of Queuing Systems, and the other is Stochastic Optimization with Application to Communication Queuing Systems. Prerequisite for this course would be probability statistics process, stochastic process, basic idea of queuing system, elementary calculus, and so on. So first we introduced what a queue is. So a queue is a virtual stack or some a form of line where people wait so that they could get some service out of some uh, counter or some server. So you have people arriving to that queue so that they can get their service done. And the arrival rate is so the arrival is modeled as a random variable or a random process. And then you have the server because each customer would have different requirements. So his the time that the server takes for each customer would change. So that is also modeled as a random process. Mm. So basically, if you define these two things, where uh, if you define these two things, uh, then you're basically defining the queue. There are other things also which we'll look at later, but initially we'll look at the arrival rates of the uh, people that are coming into form a queue and the service rates of the server. Right. You could also look at inter-arrival distributions. You could also look at inter-service distributions. You could look at queue disciplines and we'll talk about them later. Okay, but first we'll talk about what we spoke yesterday about what this course is going to talk. So talk about this course will teach you optimal design of queuing systems where you make some decisions so that some requirements of the queuing system are being met. So you need some latency requirement, you need some throughput requirement, you need some waiting time requirement, and so on. So if you have these kinds of requirements, yeah, and now you are assigned to design a queuing system, then you need to know what are the parameters that I can tinker around so that mm, I achieve those requirements, right? So basically, while designing a queuing system, you need to make sure what are your decision variables and what are your known variables. So all the variables that you'll have mostly in queuing systems are either your arrival rates, your services, or scheduling policy. Scheduling policy tells is a set of mm, decisions that the server makes, uh, which basically chooses which arrival to be served. So if one example of scheduling policy is he could choose the first arrival who has arrived to serve first. So that would be a first come first serve, first out FIFO service. He could choose to do the mm, shortest job first service or something similar. So there are many scheduling policies which we'll look at later. Next is the cost and benefits. So each mm, requirement that you meet of for the um, each requirement that you meet uh, that you need to meet of the queuing system that could be formulated as a cost function. And now based on all the cost functions you have, you formulate an objective to either minimize or maximize the cost or reward. So you minimize the cost that you incur or you maximize the reward that you incur, right? And the next thing is so we'll not only talk about design of queuing system, we'll also talk about control of queuing system. So design of queuing system is basically the parameters will be given to you. Uh, and once the parameters are given, then everything is fixed. And now choose, you give the optimal parameter that needs to be set for these set of parameters so that uh, you can run the queue for a long amount of time and your required reward or cost is being met, right? Now, control is something where you take dynamic decisions. So basically, design is static and control is dynamic. So the dynamic decisions in the dynamic decisions place, what we'll do is we'll time slot the whole process, and then at each slot some Poisson random Poisson arrival number of the so at each slot there'll be a random number of mm, arrivals would occur, where the random number is modeled by a Poisson random variable, right? Okay, so next we have you could look at it for a finite horizon or infinite horizon. We'll be mostly looking at infinite horizon times. And yesterday we saw uh, we saw we fixed the queuing model to be MM1. So where the first M denotes the arrival process, the second M denotes the service processing, the third number denotes the number of servers that are used in the queue. So M is a Markovian arrival. When I mean Markovian, I mean that so the arrivals follow a CTMC process, and um, CTMC process, you have inter-arrival distribution between two arrivals to be exponentially distributed. So the inter-arrival distribution is modeled by a random variable whose distribution is exponential. Similarly, the service also is done by the same thing, where you model the service by Markovian. Markov CTMC, you model the service by CTMC, and one means that you have one server there, right? Infinite horizons will use steady state analysis for design and time average for time slot step. That is one month. So yesterday the main thing that we saw was optimal service rate, MM1Q. Now to give the MM1Q, we need to give the rates of the arrivals and the rate of the service. So we'll assume that the arrival rate is lambda and service rate is mu. So yesterday for optimals to get the optimal service rate, we fixed the arrival rate. We wanted to find the service rate, right? So customers arrive according to Poisson process with rate lambda, and uh, um, the service time that each customer gets is modeled by a random variable x with mean 1 by mu. So that x is a exponential distribution again. Then we defined two cost functions. So one cost function was the service cost. So when you allocate new amount of service, so what you're doing is you're allocating resources so that the customers could be served. And once these customers are served, to allocate the resources, you're spending some amount of cost. You incur some cost uh, to allocate those resources. The more the resources you allocate, the more the cost you spend. So we model the service cost as linear, where you have the linear rate to be C, right? So if you choose mu as a service rate, then the cost that you incur to allocate new amount of resources to the server or to the customer is C into D. It's linear, right? Waiting cost, which makes sense. Waiting cost. So waiting cost is a cost which the customer sees first, but the system also sees. So the more the customer waits, the more uh, he gets frustrated and he doesn't want to use it again. So that is the more you make a customer wait, you are incurring a cost of making him wait more, right? Because he's occupying some amount of some physical queue or something in you. So we model the waiting cost also to be linear with rate h. So if a customer waits for time t, then the customer cost that he pays is h into t, right? Now, if the customer cost is HT, but now the waiting cost that the system pays is basically in an unit time. So now here we are not discretizing the um, time scale, but we are taking a unit time. In a unit time, if there are I amount of customers, then each of them would pay one. Each of them it would cost 1 unit, right? So total of I into H is the cost of the total system. Okay, so I hope this is clear. The HT, this is the cost to the customer, and this is cost to the system. right? Okay. And then using the basic queuing definitions, we see that arrival rate less than service rate lambda less than mu is when you get a steady state. If lambda is not less than mu, you don't get a steady state, which makes sense because if your arrival rate is greater than the service rate, then basically you have more people coming in than you can serve. So the queue keeps on increasing and it blows up to infinity. So now you define two cost functions. Using these two cost functions, we'll define the objective function. The objective function, we defined it as sum of the service cost and the waiting cost. So C mu plus H into, uh, H into I. But this objective function, we are defining it at the steady state with expected total cost of the system, right? So you have expectation of C into mu. Since C and mu both are just numbers and not random variables. The expectation of C mu is C mu plus expectation of H into I. I is the number of um, customers in the system. Now that is a random variable. So at each slot, you'll have different number of um, people. So now we need to find the expected number of customers in the system. For that, we went back to basic queuing systems for MM1 queues and got the closed form solution for L. L mu is the um, L mu is the uh, expected number of customers in the system, which is given by lambda by mu minus lambda, right? Which makes sense. So suppose lambda increases. Sorry, suppose mu increases. You know that mu is greater than lambda. So the denominator decreases. The whole term increases. Whole term decreases. So mu minus lambda, mu increases, and we know that mu is greater than lambda. So denominator increases, the whole term decreases. So as you keep on increasing the service rate, the expected number of customers in the system would decrease because you're not allowing the customers to wait in the queue. You're serving it at a much higher rate, right? Then we modeled MM1 queue as a birth-death process where you had states. The states indicate the number of customers in the queue. And based on the number of customers in the queue, and based on number of customers in the queue, uh, and based on number of customers in the queue, uh, so suppose there are zero number of customers in the queue, right? Then with rate lambda, you go to state one. So with rate lambda, some new arrival occurs. Similarly, with rate mu, with rate mu, you go from 1 to 0. So mu is the rate at which you serve. Then you go from 1 to 0, right? So you decrease. So at rate mu, you serve a customer. So that indicates a death. And with rate lambda, a new arrival occurs, which indicates death. So you model MM1 queue as a birth death process, right? Next, we want to calculate the expected number of customers in the system. So basically, you want to calculate the probability of you staying at each state. So we define Pn as the probability that you are in state 0, P0 as probability that you're in state 0, P1 as probability you're in state 1, Pn that you're probability in state n. So the whole flow of the proof is whole flow of finding the closed form solution, analytical solution of expected number of persons in the queue is you find Pn, then you calculate summation n into Pn, which is basically the expectation of number of customers in the system, right? So we discussed one method where we wrote the barrier function method. We defined the barrier and the flows through the barrier, flows into the barrier, or the flux into the barrier is equal to the flux out that outgoes from the barrier. That needs to be the same. So you have P state P0, you stay at state P0 with probability P0, and you go to state with rate lambda. So it's P0 into lambda, that is equal to you stay at state 1 with probability P1 and you go to 0 with mu. So P0 lambda equal to P1 mu. That gives you a relation between P1 and P0. Similarly, you go to P1 and P2 and iteratively put the definition of P1 there. So you get all the Pn's in terms of P0. You get Pn equal to P0 into lambda by the whole power n. Now you have to find P0, right? Because you know all the Pn's in terms of P0, but you don't know what P0 is. So since this is a distribution, you can you can uh, you can say that the summation of all the probabilities should sum up to 1. You use that and you see that you get a geometric progression series. You use the infinite series formula for that, and you get the value of P0 to be mu minus lambda by mu. Now, mu minus lambda by mu is a big thing to remember. So we introduce a new term known as rho, which I'll be calling from now on the utilization factor, right? This is the utilization factor or the load to the system. Any two of these terms I'll be calling rho. Now, rho is defined as lambda by mu. Since we know that mu is always greater than lambda, mu will be a fraction which will be between 0 and 1. So based on that, we can write P0 as 1 minus rho, right? Now we found out Pn and we saw that it follows a geometric distribution. Now the expectation of geometric distribution is failure probability by success probability, and we write that and we get the closed form solution for the same. Similarly, we can use generating functions and difference equations to find the probability distribution of the state and so on, and so get the expected number of uh, right. But to write the generating function and difference equation, we needed to write the balance equations at each node, not at a barrier. So at each node, you'll have uh, flow coming into the node and flow going out the node. So flux or rate of flow coming into the node should be equal to the rate of flow going out of the node. You can't have uh, more flow going out than coming in. If you use the same similar um, equations that we did for the barrier method, but now on a node, not on a barrier, you'll get the following equations, and using these, you can derive the you'll get the same closed form solution for the expected number of customers in the system for n and 1q. Right. Next, we have the objective function. So we have, okay, we digressed for finding the expected number of people in the customer. The objective function was given by C into mu plus H into lambda by mu minus. Now, our goal is to minimize this objective function with the constraint mu greater than lambda, right? Which is equal to k mu. Now, what we do is we just find the derivative of the objective function, and before equating it to 0, we just check whether the optimized problem that we are solving is um, a convex optimization or not. So we take the second derivative and see that it's greater than 0. For the case where mu greater than 0, and that is what our constraint set is, or the set is, so we are safe. So in the state mu greater than lambda, we are in a convex optimization problem zone, and equating it to 0 would give you the optimal value. And at that optimal value, we saw how the service cost and waiting cost and the total cost vary. So what we observe after seeing that is mm, the service cost keeps on increasing as you keep on increasing service rate. The waiting cost keeps on decreasing as you decrease the service rate. But at one point, you'll see that the service cost and the waiting cost are equal, right? Uh, that is a At that point is where you'll get the optimal. This is not true for, so basically you have two costs, sum of two costs. The one cost is increasing and other is decreasing. At that time, the optimal solution is to try to equate the two costs, but that is not always true. It will be true if the first cost and the first term and the second term, the increasing term and the decreasing term are, the first term is linearly increasing and the second term is linearly decreasing, right? If you take care of this, if you have this kind of specific scenario, that is when you can see that the both the costs are equal at the optimal rate, right? Next, we substitute back the optimal service rate to the objective in the objective function and found that optimal cost objective function, which or optimal cost, which gave us, you had one basic minimum cost that you need to put, that is c lambda plus root hc lambda plus root hc lambda. Now root hc lambda and root hc lambda are service cost and waiting cost, both are equal here, right? So we just wanted to see how far mu star is from lambda that we are taking. So we uh, initiated a new variable mu tilde, that is mu tilde equal to mu minus lambda, which implies, and we reformulated the same optimization problem again and calculated the same things. The first derivative, the second derivative, we show that is greater than 0. So again, we are in the converse optimization region. And we equated first derivative equal to 0. We got a mu star tilde. Yeah, we stopped here, right? So today we will talk about optimal arrival rates. Right. So again, we'll consider the MM1 FIFO system. But now here, service rate is fixed. The service rate mu is fixed, and arrival rate lambda is unknown. So this is your unknown or decision variable, and this is your known variable. Yeah. So I have a service rate mu, which is fixed, and arrival rate lambda, which is the decision variable. So some example is at what rate lambda should you send the messages to a buffer so that you get some requirements that you need to be right. And the performance measures and trade-offs here is as lambda increases, the throughput increases. So the number of jobs served per unit time increases, right? Because you have more number of things to serve, you will be able to serve more number of things, right? That is for the case when lambda is less than mu. If lambda is greater than mu, then you'll have a huge amount of buildup and your number of jobs in the queue would go to infinity and you'll have congestion, right? But on the other case, even if lambda is less than mu, uh, you'll increase the congestion, right? Once you increase the congestion, you'll increase the waiting times, and this is a bad thing, right? So again, we'll model it as a simple linear model between two performances, but instead of cost, we'll use reward functions to model, right? So you have the more customers that you get is a good thing, right? So as lambda increases, you get rewards because you get more customers. More customers, more the payment that you get. So one is the customer reward. This is linear with rate R, and you get lambda into R, right? The second one is um, the waiting cost, which is again linear with rate H, and which is similar to the last time, HI customer cost and HT customer cost, HI system cost to the system, right? Now using these two, we'll design the objective function. Yeah. So now the objective function, I'll denote it with b of lambda because lambda is a decision variable. This you get it as lambda r minus. So now since one is a reward and one is a cost, you both are in the opposite thing. So you add the reward and minus the cost, and you maximize the total reward. Or you could do reward minus cost and minimize objective function, which is one. Both are the same things. But if you have both costs, then you add the cost and minimize cost. Right? I hope that is clear. And here you get um, h into L lambda. L lambda we have derived earlier, which was lambda by mu minus lambda. So this remains same. H into lambda by mu minus lambda. Right? And we know that lambda should be less than mu. If lambda is not less than mu, then the long run average cost goes to infinity because this term goes to infinity. Right? Uh, Now, since this is a reward based thing, we'll maximize instead of minimizing. Right? So the optimization problem that we are trying to work on would be maximize b lambda such that lambda belongs to 0 comma mu. Right? Now you can't choose lambda which is negative because you can't have negative arrival rate of customers. That means that your someone is going out of the server without even coming in. So it doesn't make sense physically. So you have one more constraint than the previous one. In the previous optimized problem, what we had was we had mu greater than lambda. We had one constraint. Now we have two constraints basically. So you have max b of lambda, you have lambda greater than or equal to 0 and lambda less than 0, right? So now as lambda tends to mu, we see that b lambda tends to minus infinity, right? As these both get closer, this term goes to 0. As this term goes to 0, this whole term goes to infinity. So this whole term goes to minus infinity, right? So as lambda tends to mu, we see that b lambda tends to minus infinity, right? So we do not need to concern ourselves about the upper limit of the feasibility, but uh, we need to take into account that there could be possibility where the maximum, because we are looking at the maximum occurs at some lower limit, such that in cases where it's lambda equal to 0, right? So if lambda equal to 0, you will see that the cost function goes to 0, right? So you have uh, at one end of the spectrum, you have bounds on lambda. The lower limit of lambda is 0. If you substitute 0, you get to 0. If you substitute mu, you get minus infinity. So basically what you have is, uh, suppose this is your lambda and this is your objective function b lambda, and this is 0, this is 0, this is mu. At mu, we know that Vt is going to minus infinity, right? And we know that at 0, it is 0. So you could have a case where this could be the curve of Vt. If this is the curve of the Bt, then the maximum is you get it as lambda at lambda equal to 0. But you could also have a case where you have a curve like this. And now this curve implies you have a maximum here. So it all depends on how you start at 0. So are you increasing at 0 or are you decreasing at 0? But before doing all this, we need to see that if the gradient is decreasing from 0 to mu 1, right? So what I'm talking is gradient is decreasing. So the gradient of the gradient, that is what we want to find out. So first we calculate the derivative of b lambda with respect to lambda, which will give you r minus h into mu minus lambda minus plus 1 by mu minus lambda plus h lambda whole square. Right, so you have r minus h lambda cancel, h mu by mu minus lambda whole square. Now you get the second derivative, you'll get h mu by minus mu minus lambda whole cube, right? 2 into. So as you can see, the double derivative is less than 0 because mu is greater than lambda and h and mu are greater than 0. So this is less than or equal to 0. So you have a decreasing function. At least in the range 0 to mu, because it's not decreasing function. Your gradient is decreasing, right? So your gradient is decreasing. So basically your gradient is decreasing. So that is what this implies. So you have a basically a concave function. And since you're maximizing, concave function implies that you'll always have a um, maximum. Okay, so the maximum either occurs at lambda equal to 0, as seen by this picture, it occurs at lambda equal to 0, or some point, some unique value of lambda which is strictly greater than 0, right? So case 1 is you find the optimal at 0, that is if v dash of 0 is less than or equal to 0. So if you have a negative gradient at b0, that means you're going down from 0. So you'll never come back because the gradient is decreasing on this, right? But if you have a positive gradient at 0, if you have a positive gradient at 0, then you'll get some optimal value. We need to calculate this optimal value, right? So first, gradient at 0. So we know that b dash tilde equal to r minus h mu by mu minus lambda whole square, and gradient at 0 equal to r minus h by mu. So if this is less than or equal to 0, right, which implies r is less than or equal to h by mu, which implies mu is less than or equal to h by r. So your optimal lambda star equal to 0 if r is less than or equal to h by mu, right? And um, b dash lambda equal to 0. You get the lambda star. You get the lambda star at this value. So this comes out to be r equal to h mu by mu minus lambda whole square, which implies mu minus lambda whole square equal to h mu by r, which implies uh, mu minus lambda equal to root h mu by r. And now since you're finding lambda, lambda equal to mu minus root h mu by r. Okay? This is basically lambda star. All these lambdas are lambda star. So lambda star equal to mu minus root h mu by r if r is greater than h mu. So these two cases I'll again illustrate through a graph once again. So you have your arrival rate lambda and your reward or costs, right? Next, we are on the reward. So reward is linear, right? So as you increase your arrival rate, your reward increases. Okay. Next is cost of waiting. So cost of waiting, we know that you can go only till mu, 0 and mu. The closer you approach mu, the more you have to wait. So basically, lambda, the closer that lambda is to mu, the more you have to wait. If lambda equal to mu, the waiting cost goes to infinity. So basically, you have waiting costs. And if your lambda is zero, then your waiting cost is zero because you don't have any arrival. So there are the null hypothesis. There's no one to wait. This is your cost of waiting, and the total, if you add this up, you'll get something similar to this. Right. So this is one case where this could happen. The other case is, so this is the case when um, R is less than or equal to H by Q. If this happens, so what does this mean is the reward that you get to get the customers or to get customers is not high enough, then we you have a threshold. So if the reward that you have given is very less, then you'll never beat the waiting cost that you occur with even a small amount of arrival. So what you need to do is you have reward and costs. Okay. Now if you increase the rate of your reward and you have mu and zero, right? Now the waiting cost would remain the same because you've just changed the reward that you get for each arrival. This would remain the same. But the net cost, this would see a jump because you have just increased the reward that you get per serving per customer. And because of this, so this case occurs if R is greater than H by mu. And if this occurs, then you see that you get a maximum value, right? So uh, now, if I write down the optimal solution, as you can see here, the optimal lambda star equal to mu minus root mu h by r, right? And as you can see, if r is less than h by mu, then uh, this lambda star is greater than zero if and only if r is greater than h by mu. This case, right? If it is this case, then you can see that lambda star is less than zero. That is what you get. So we can write lambda star as max of mu minus root mu h by r comma 0 or lambda star equal to mu minus root mu h by r plus, right? So so what we have seen is in case one we have h by mu is greater than or equal to r, that is expected waiting cost is at least as great as the reward even for a customer who enters service immediately. Hence, it is intuitive. So you need to make the reward as high as possible, not as high as possible. You need to design such that the reward that you give for each customer that enters the service, so that the expected waiting cost is it is greater than at least the expected waiting cost when even one customer enters, right? So it is intuitive here in that region why lambda star is zero. So there is no economic incentive to even admit a customer because your waiting costs are so high than the reward that you get for being able to serve a customer. So you have this internal notion of how do you design the reward so that you can allocate some lambda, right? So next we will discuss um, social versus individual optimization. So till now, what we have discussed, we have discussed two things. One is optimal service rate and optimal arrival rate. In both the discussions, we saw that uh, we mainly implicated that there is a decision maker who is the operator of this queuing facility, and he is deciding what either mu should be or lambda should be, right? Who is concerned with both maximizing throughput and minimizing congestion in the queue. Our reward cost models that we all have modeled assumes these things. So assumes that each customer that enters the queuing system generates some reward to the facility and also utilizes some resources. So it incur some cost to the facility. Now the facility wants to maximize the rewards that he gets by getting more customers and also giving the bare minimum amount of service that he can give so that he can keep the customer satisfied. Right. But there could also be the alternative possibility for who the decision maker could be or might be, right? So uh, uh, this is one question. So one question is, who is the decision maker? Second question is, um, in the second problem, like in the problem that you've seen today, the optimal arrival rate, we have assumed that uh, the decision maker, even if he is the one who runs the queue, how can he freely choose an arrival rate lambda in the between the interval 0 and right? How could he implement something like that? So what one could do is suppose he sees a total influx of capital lambda as arrival rate, and arrival rate is something which is greater than or equal to mu. So a potential customer, what he does is he accepts a customer with probability A and rejects a customer with probability 1 minus, right? Now, basically, you want to design A such that you want to design you the if the so the second question we are talking of is in the case if the decision maker is no is the guy who is running the queuing system, is not the customer, right? So decision maker could be the customer or could be the guy who is running the queuing system. So uh, now we have a customer who enters with probability A. Uh, so now you have the arrival rate with lambda A, right? Now, how would the reward structure change if you implement these kind of things is you'll if a customer enters the queue, you'll get a reward structure based on A into R minus H W lambda, where W lambda is a weighting, plus 1 minus A into 0, which is equal to A into R minus H W. So the 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 previous problem goes through because but you need to also make a decision of what the A is. Mm, and you can replace the whole lambda and you can reformulate the whole problem. But the second question that we have answered right now is taking into consideration that the decision maker is the guy who's running the queuing system and not the customer. But it could also be possible. The question is, could the customer also be the decision maker? So would the customer be the decision maker is the customer comes with some probability, he decides to go into this queue, get served, or with probability 1 minus a, he doesn't get served. Now, how should the decision be made? Should it be social or should it be individual? Like each customer should he see his own benefit, or is there a guy who delegates, who does not belong to the guy who's running the queuing system, but also does not belong to the customer? So a third party who just wants to benefit all of the customer in average, but not each person. So, so what I mean by that is, okay, so first let's look at socially optimal arrival rate. So socially optimal is the benefits and costs that each individual customer that gets. The decision maker is not the guy who's running the queue. It is not the customer, but some guy, a third party, who sits on top of all the customers and makes a collective decision rig base calculation for the customers, right? A reasonable objective for the decision maker is to maximize the expected net benefit that each um, customer receives. So it the whole problem formulation is just same as what we have just done right now. So you have b lambda, this is your objective function. You have lambda into r minus h into 1 by mu minus lambda, right? Mm, And the choice of lambda still makes sense because you can the decision maker is acting on behalf of the collective. So what he'll do is he'll admit uh, so now you have solved the previous problem that we have solved today. You have found lambda star, right? Now, once you have found the lambda star, what the guy who is sitting, who is elected by the collective customers to maximize their optimal rate reward, what he does is the decision he does is he chooses A equal to lambda star by capital lambda. He knows the rate at which arrivals are coming. He knows what is the optimal arrival rate. Now he divides those two, he gets a A. Now with that probability, he allows the customer to go in or rejects it. With one probability 1 minus A, he rejects the customer, right? Now this A is basically a socially optimal uh, because it maximizes the social welfare. And you will see that this social welfare is just same as mu minus root over mu h by r, which we have seen today, plus. And you can calculate as lambda s by delta. I'm just using this S notion just to show that this is the socially optimal arrival rate, and which is same as what we have done today. But in other cases, due to some design issues, it might be different. But for this case, it is the same thing, right? Now, individually optimal arrival rate. So, individually optimal arrival rate. So, it's the same case. Potential customers arrive according to person process with arrival rate capital lambda, and each join the system with probability A and does not join the system with probability 1 minus. Now, each customer who enters the system when the arrival rate is lambda receives a net benefit of R minus H W lambda. A customer who does not enter receives nothing, right? Since the so this is the reward if a customer enters, and this is the reward if customer does not enter. So what will happen is based on how you define the rewards, you will see that uh, customers will join with probability A equal to 1 if R is greater than HW, because you're getting something, right? But this is all the customers will join. And customers will not join, that is A equal to 0, if R is less than or equal to HW, right? Well, it's less than, and if it is equal to, if R is equal to HW lambda, then it doesn't matter. Both would get the same cost. So any probability distribution would work fine, right? Okay. So next we'll introduce a concept called as Nash equilibrium. And we will define an equilibrium arrival rate. Lambda E, where the property of this equilibrium is no individual customer trying to maximize its own expected benefit has any incentive to deviate from lambda E. So here what I'm doing is, instead of letting customers take a decision because it will always be selfish, and designing, I'm telling customers, okay, you follow this method, that lambda E that I'm going to give them. Using that lambda E, they can generate an A, and with probability A, they can find some, they can either join or not join. Now, with that probability, no individual customer will try to deviate from this policy, right? Because if he deviates, then he'll be worse than what he was because of what the other people are going to. So, uh, but in this case, it will remain the same. So lambda I would be 0 if that is A is 0, if R is less than or equal to H W 0. Uh, but when R is greater than HW 0, then lambda E would be equal to A lambda, which is the unique value. And if R is equal to H into W lambda, right? So for this case, it doesn't change much, but yeah, uh, we'll come back to this in other different type of models. Okay, so next we'll see optimal arrival rate and service rate. Okay, so I'll just do a quick recap of what we did today. So today we saw optimal arrival rates for MM1 FIFO system where service rate is fixed and arrival rate is not known. We defined two reward functions. One is the customer reward and one is the waiting cost. We define the objective function, which is a sum of your reward and cost. Because it's sum of the reward and cost, you add all the rewards and you subtract all the costs, and you will then maximize the reward. Or you could do is add all the costs, subtract all the rewards, and minimize cost. Okay, the previous one was maximize rewards and minimize cost. Okay. Mm. Next, similarly, in the similar method we did last time, we formulated an optimization problem by maximizing the reward. But now the constraint for lambda is it should be greater than 0 and less than 1. So there are two constraints, greater than 0 and less than 1. We saw that it is a concave optimization problem in this region, but we had a problem that the optimal function could be 0. So you could say that don't tell anyone because of some things that happen. But intuitively, what we saw is if you make the reward less than a threshold, then due to less reward, you are not incentivizing a customer to get service at all because the reward to get service is less than the penalty that you have to pay to wait, even if there is a very tiny amount of customers, right? So you need to fix the reward of a customer to get service upper than a threshold. So we found that threshold. That threshold is um, h h by mu. So you have to give your reward greater than h by mu, where h is the waiting cost rate and mu is the service rate. Then you get the optimal arrival rate, which is mu minus root h mu by r. Okay. We saw graphical representation of what does it mean when I say that when r is less than h by mu, and what does it mean when I say r greater than h by mu, what happens to all the cost functions that we have defined there. Right. Next, we saw something known as social versus individual optimization. Social optimization is we didn't talk about the part where who is the decision maker. Is it the customer decision maker or the guy who is running the queuing system is the decision maker? Hmm. That was one question we answered. So if it is the guy who's running the guy who's running the queuing system is a decision maker, if that guy is a decision maker, then what we did till before this part makes sense. But if it is the customer, then we have to answer the question whether each customer is making the decision for his own good, or is there someone collectively who is making decision collectively for all the customers so that the expected number of customers such that the expected cost of the customer or the expected reward that the customers get is maximized. So that is one more question that we need to we answered. So basically, the it is either socially or individually. So if it is socially, so there is a guy who is not running the queuing system and who might be one of the customers, but who takes decision on behalf of all the customers so that the uh, expected reward that each customer gets is maximized. So what we found that the socially optimal um policy is the same policy as when the guy who runs the queuing system takes the decision. Then there is this individual um, individual optimal arrival rates where each customer takes self-decision of whether to join the queue or not join the queue, right? So yeah, so we'll stop it for today here. In the next class, we'll see what happens if we consider an MM1 queue in which both the arrival rate and service rate are not fixed, both are decision variables. Then um, what the reward cost model would be, what are all the cost functions that would come up now, and what is the objective that we want to do. And now this will become a multi-dimensional optimized problem, because till now we had just one decision variable, but here we'll have two decision variables. Then we'll see how to optimize in that, and how to show whether optima point even exists for that case or not. Right. Yeah. Stop the recording.